Good afternoon, good morning, good evening to everyone, and welcome to another in a series of virtual Secretary of the Navy guest lectures. My name is Frank Narducci, and I'm a professor of physics here at the Naval Postgraduate School. I am super excited to get to our lecture today, but before I turn the microphone over to our president to introduce today's speaker, I would like to take this opportunity to highlight a few things going on here at NPS in the field of quantum technology, in particular as it pertains to our current speaker. First and foremost, I would like to highlight two upcoming panel discussions as part of NPS's Sea-Power conversations. Our first one is going to be held on the 23rd of February from 10 until 12 PST, and it will be focused on a discussion of quantum sensors. The second one will be held on March 2nd, again from 10 until 12 Pacific, and will focus on quantum computing. These workshops are going to feature 3 to 4 subject matter experts in their fields who will first highlight their work and then will give their views on the status of the technology. Following their comments, the workshop will feature an extended Q&A session with SESers, flag officers, and senior government officials. You're all welcome to watch the live stream event, either in real time or in a recorded session, by following the link posted on our NPS website. Inquiries can be directed to me at frank.narducci@nps.edu. Secondly, I'd like to mention that there's a lot of activity in the general field of quantum information science right here at NPS. Atoms, those wonderful building blocks of everything, are super useful for making measurements for a variety of reasons. In particular, atoms and gases are very nice because they hardly interact or hardly talk to each other. However, they tend to like to zip around at speeds at or above Mach 1, which gives experimenters very little time to make measurements. Our speaker of today has shown how one can take a laser and actually slow these atoms down to a crawl to allow time to make precise measurements. So researchers around the world, including us here at NPS, have taken these techniques and applied them to making measurements such as acceleration and rotation for inertial navigation, magnetic field forces for magnetometry, and time for precision timekeeping. We here at NPS have several lab experiments designed to help transition this technology from the laboratory to the operational environment. For today's events, we have the talk followed by a Q&A session led by 4 of our very own NPS students that we will be introducing later today. However, for those watching the live stream event, there's a link in your window that will allow you to submit questions to us in real time. We welcome and we encourage your questions, and the speaker will try to answer as many as he can in the time allotted for today's session. So with that, I would like to turn the microphone over to our President, Vice Admiral Rondeau, who will introduce today's speaker. Over to you, man.
Thanks, Frank, and good afternoon, good evening, good morning to everyone. I am Vice Admiral Ann Rondeau, President of the Naval Postgraduate School. I am delighted to have the distinct honor to introduce today's Secretary of the Navy guest lecturer, Dr. William D. Phillips. Bill graduated summa cum laude from Juniata College in Pennsylvania with a Bachelor of Science in Physics in 1970. He went on to receive his PhD in 1976 from MIT under the direction of one of the most well-renowned, well-respected, and international heroes of atomic physics, Dr. Dan Kleppner. After a 2-year postdoc at MIT, Bill joined the staff at the National Institute of Technology and began his remarkable research career. Over the years, he has won numerous awards, way too many to list, but among those that are notable was his election to be a NIST Fellow, the winner of the prestigious Michelson Medal of the Franklin Institute, election to the National Academy of Sciences, accommodation to the Pontifical Academy of Sciences, the Presidential Rank Award, and the Service to America Award. As you have already heard, Bill was, and still is a pioneer and a leading researcher in the field of laser cooling and trapping of neutral atoms. His research has led to new kinds of measurements and processes, such as high-resolution spectroscopy, atomic clocks, atom optics, and atom interferometry. His work led to his being awarded the Nobel Prize in Physics in 1997 for, quote, development of methods to cool and trap atoms with laser light. He found that atoms could be cooled far below what was then believed to be the cooling limit. So, in some sense, Bill won the Nobel Prize for the experimental demonstration of an extreme violation of Murphy's Law. Without further ado, I give to you Dr. Phillips. Bill, over to you, sir.
Thank you very much. Now I'm going to try to share my screen, and let's okay. Well, anyway, that's not quite where I want to be. There we go. Anyway, President Rondeau, thank you very much for that very kind introduction. It really is a pleasure for me to be here virtually, and I'm really looking forward to being with you in person, hopefully about a year from now, where I'll be talking more about some of the things that you mentioned in your introduction. But today, I want to talk to you about the revolutionary quantum reform of the metric system. And I want to point out that I am a member of the Joint Quantum Institute, which is a joint operation of the National Institute of Standards and Technology and the University of Maryland. And at NIST, I'm a member of the Laser Cooling and Trapping Group. Gretchen Campbell is its group leader. Paulette, Trey Porto, Ian Spielman, Ida Tietzinga, and Charles Clark are members of that group, and I'm honored and privileged to work with them on a regular basis. A lot of the work I'm going to be telling you about was supported by NIST, and some of the really important work I'm going to be telling you about was supported by the Office of Naval Research. And what I'm telling you is under the sponsorship of the International Union of Pure and Applied Physics, which is an organization that promoted the institution of the modern metric system back in 1960 and has been supporting it ever since. So, what is this revolutionary quantum reform of the metric system? Well, on the 20th of May of 2019, we underwent the biggest revolution since the French Revolution in measurement. And the nature of that revolution was that the international system of units, the modern metric system, was changed in a dramatic way. The international system of units bases all measurement on 7 base units: the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela. And today, all of those base units are now defined by fixing values of fundamental constants of nature. Now, in order to understand how this can be done and how an earlier unit of measurement, namely time, made use of this, and with apologies to the late, great Stephen Hawking, I'm going to attempt to bring you my version of a brief history of time. Since we have had seconds, a second was 1 day divided by 24 times 60 times 60, or 1 day over 86,400. Now, that was wonderful. Everyone knew what a second was. But since around 1900, we've known that the rotation of the Earth, the thing that sets the length of the day, changes from time to time by an amount that by 1900 it was possible to measure. And that represents a problem, because you now have what is supposedly a standard of time that is itself variable. And that's not something that you want. Well, people worked on this problem, and by around the middle of the 20th century, people were making atomic clocks. Here's a picture of an atomic clock using the ticking of a cesium atom at the National Physical Laboratory in Great Britain. And this clock was much better than the Earth, by something like a factor of 1,000 better than the Earth. So it was clear that you had to do something to the definition of the second. Earth rotation metrology was insufficient for the needs of time metrology. Atomic timekeeping had given us a technology now more than a decade old, so that in 1960, people decided to redefine the second to be a fraction of the tropical year 1900. What were they thinking? The tropical year 1900 does have the advantage that it never changes, but it's not exactly readily available for measurement today. Well, finally, people got smart, and in 1967 and 68, the General Conference on Weights and Measures adopted an atomic definition of time. The new definition of time is that the second is the duration of some 9 billion periods of the radiation that corresponds to the transition between two energy levels in the cesium atom. And these cesium clocks just kept getting better and better. They stalled out at about a part in 10 to the 14. That's incredible. The Earth has variations on the order of a part in 10 to the 8th. So this is 6 orders of magnitude better than what was possible with the Earth. But why did it stop at part in 10 to the 14th, as good as that is? It was because of just what Frank Narducci was telling you at the beginning, namely that the atoms are moving around really fast, something close to the speed of sound. Laser cooling addressed that problem and allowed these clocks to improve by almost another 2 orders of magnitude. So these clocks were good to a few parts in 10 to the 16th. Among some of the best of those clocks are the clocks that have recently been installed at the U.S. Naval Observatory, the timekeeper for all of the U.S. military. And here I am at a ceremony celebrating the introduction of these clocks into full capability. Chris Ekstrom, who was the head of the project at the time, Steve Peel, who was one of the major scientists at the time, both of these people were postdocs in our laboratory at NIST. And I'm so proud that they were in charge of making this wonderful revolution at the Naval Observatory. This is Bobby Junker, now sadly passed away, who was the guy at the ONR who funded my work starting in about 1980 to develop the techniques that made these clocks possible. So that was a wonderful time. But I want to now remind you of the key concept that is represented by what you see here in this picture. We had an arbitrary artifact, the rotating Earth, that had a rotation that could change for any number of reasons. The tides, earthquakes, changes in sea currents can all change the rotation rate of the Earth. And that artifact was replaced by something that's truly a constant of nature, namely the frequency of a quantum transition in some atom, in this case namely cesium. That's the key concept. You've got something that isn't going to change. Why is it so important? Well, one of the reasons why it's so important is the GPS system, the satellite navigation system. Every one of those GPS satellites in a constellation of at least 24 satellites has several atomic clocks on board. And by receiving signals from those atomic clocks, ships at sea, aircraft, ground-based operations can tell not only what time it is, but where they are anywhere on the face of the Earth to within a few meters, almost instantaneously. This is huge for the Navy and huge for not just the rest of the military, but the civilian sector as well. And work on making these kinds of clocks better, these things that I haven't described for you that are called atomic fountains. These atomic fountains, here you can see atoms being launched upward. This is in Frank Narducci's laboratory. Experiments being done by Jeff Lee, a postdoc in here at the NPS, who, by the way, is an alum of the Joint Quantum Institute and the laser cooling group at NIST, and so I'm really proud of that as well. And it won't be long before in Spanigal Hall we have the world's tallest atomic fountain. This is being planned and constructed by Frank Narducci, and this is going to realize dreams of doing atom interferometry, which I haven't told you about, but if we have a chance when I come back, I'd love to talk about that some more. And that's going to lead to better navigation, not involving GPS, but inertially. So all sorts of wonderful things going on because of time. Well, what's next? Length, a short history of length. Well, time was historically important and even more important technologically today, but in the distant past, length was really important because it involved commerce. In ancient times, the early approach to length measurements was that the human body was used as a standard. Now, this was really convenient because you always had your standards with you, but it wasn't very convenient. It wasn't very consistent. If you had a short fabric merchant, then he might be selling you a much smaller length of fabric than what you had expected. Well, how do you fix this? Well, one approach was to use a particular body. For example, the body of a monarch. In ancient Egypt, it was the length of the pharaoh's arm was called a cubit, and that royal cubit was used as the standard to build the pyramids. But it turned out it wasn't very convenient even to define the cubit as being the length of the pharaoh's arm because the pharaoh wasn't around, and you might have a different pharaoh from the time that you started the pyramids to the time that you finished them. And so they made an artifact. They made a granite rod, and that became the standard of length. And using secondary standards calibrated against that granite rod, they did a magnificent job of making the pyramids to incredible accuracy, considering the time in which they were working. This idea of making an artifact was something that spread throughout the entire world. All over Europe, there were artifacts that were often particular to each individual town. In the town of Regensburg, there is cemented into the walls of the town square lengths of a foot and of a cubit and of a fathom. And here you can see that this fathom of Regensburg is a particularly good long one. This was probably a good place to buy fabric. The problem was that these were different from the standards of surrounding Bavaria. And this was a vexing but common problem throughout Europe, that as you went from one place to another, the standards of length changed. And what were you to do about this? Well, this is where the French Revolution comes in. The French revolutionaries wanted to reform everything. And one of the things they wanted to reform was the standard of measurement. And so with the French Revolution, we got the metric system. And the idea of the metric system was a new unit of length, which they called the meter, which was going to be the measure of all things. And they defined the meter to be 1/10,000,000th of the distance between the pole and the equator along a meridian that went through Paris. And so what they did was they sent out surveyors to measure that distance in terms of the old system of measurements that were common in France at the time. And then to make this a measure that would be good for the entire world. They had this dream that they would make a measurement that would be good for all times, for all people, à tous les temps, à tous les peuples. And they, in fact, cast this medal to commemorate this idea. And you see this mythological creature measuring the earth with calipers. That was the idea. Well, these surveyors spent several years measuring the earth. They came back with the results of their measurement, but people soon decided this really wasn't very convenient, and they were going to do just the same thing that the ancient Egyptians did. They were going to make an artifact. And this rod, made out of platinum, became what is known as the meter of the archives. It enshrined the measurement that these surveyors had made in their trip from Barcelona to Dunkirk, I think, to measure this fraction of the meridian and then extrapolate it to the pole and to the equator. So this became the standard of length for all of France. And some years later, in 1875, we had the famous Convention du Mètre, the Treaty of the Meter. Countries from all over the world gathered together and decided that they would adopt the metric system, and they would adopt new standards of measurement. And so they made a new meter. Now, unlike the old meter, which was the distance from end to end of this rod, the new meter was the distance between two scratches on this rod made of a platinum iridium alloy. And this became now the meter for the entire world. Agreed upon in 1875, I think it was completed sometime late in the 1880s. Almost as soon as they had this new meter, it was found that it was insufficient for the scientific purposes of the day. Using light, which French physicists and other physicists had shown was a wave, and making a beam of light sent through a beam splitter, so some of it reflects off toward this mirror and some of it transmits toward this mirror, and then the beams recombine here, you could measure extremely small displacements. If you move this mirror by 1/4 of a wavelength of light, 1/4 of a wavelength of light would be something a little less than 200 nanometers, 2/10 of 1/1,000,000th of a meter. Changing the mirror by that much would change this interference pattern from being dark to being bright. And this was to be compared to a scratch that was on this meter bar. That scratch was microns wide, and figuring out where the center of that scratch was a matter of judgment on the part of the people making the measurements. So it was clear that this way, this interferometric way, using light as the standard, using the wavelength of light as the standard, was far better than using a meter bar. And so people started to use the wavelength of light as a de facto standard, by which I mean it was not the legal definition of the meter, but it was something that was more convenient, more accurate, and this became a common theme, as we'll see as we go along. Finally, and it took many decades, the international community decided in the year 1960 that they would redefine the meter in terms of the wavelength of light coming from a krypton lamp. And that krypton lamp is depicted here as a kind of an orange-colored light that would come when you ran a discharge on that krypton lamp. And the new meter was defined as being a certain number of wavelengths of the light from that lamp. That was in 1960, the year that the laser was invented. Almost as soon as they made this redefinition, people found that the purity of the light coming from that krypton lamp was insufficient for the kind of accuracy that people were making with the much more pure light that comes from the laser. And so, same story again. Laser light became a de facto length standard. This is a picture of an iodine-stabilized helium-neon laser. It produces a red light that they would lock to a certain transition in molecular iodine, and this became the worldwide de facto, that is to say, unofficial standard of length. Everybody used this as the standard of length, but it was not in meters as defined by the International System of Units, which was still using this definition from 1960 based on a krypton lamp. So now you had these lasers that were much better, and it seemed like it was time to redefine the meter again. The most obvious thing to do would be to redefine the meter in terms of the wavelength of an iodine-stabilized helium-neon laser. Fortunately, that is not what they did. Instead, they made a more brilliant choice, and that more brilliant choice was to define the speed of light. Why is this a good thing to do? Think about this equation. The speed of light is equal to the wavelength of light times the frequency of the light. What that means is that if you can measure the frequency of the light, which by the mid-1980s you could, if you could measure the frequency of light, and if you define the speed of light, then you immediately know what its wavelength is. And it doesn't matter if somebody makes a better laser that has a more pure light, if somebody devises a better way of measuring the frequency. This process of defining the speed of light and using this basic relationship will still give the definition of the meter and an improved definition of the meter as you improve the measurement of frequency and the purity of the wavelength of your light. So the new definition of the meter was this, that the meter is the length of the path traveled by light in vacuum during a time interval of 1 over this number. That's essentially defining the speed of light. And this is a really beautiful definition. Think about what this does. We went from an artifact, just as we did in the case of the Earth. Now the artifact was a bar of metal. We went from that artifact to an atom, krypton, a particular atom, a constant of nature. But we went from that to a fundamental constant of nature, the speed of light. And what that meant was that if you found an atom that was better than, or even a molecule that was better, then the definition would still be good. You would never have to change this definition again. And that has been the case. Since that definition was changed in the 1980s, we have never needed to change the definition again. When people developed, and they did, better ways of measuring the frequency of light, when people developed better lasers, and they did, this definition was still good. Well, this definition is both beautiful and brilliant. And on the 20th of May, 2019, the international metrology community brought this same beauty to the definition of the kilogram and to the ampere, the Kelvin, and the mole. Why did they have to do that, and how did they do it? Well, for that, I'm going to give you a light history of mass. As with so many things in ancient times, the unit of mass was based on an artifact. This is a set of Babylonian stones that were used as a mass standard. And these artifacts had the same kind of problems that so many artifact standards have, that they varied from one place to another. So, come the French Revolution, we're supposed to change everything. The meter, being the measure of all things, was the basis for defining a new standard of mass. A cubic decimeter. So we take a cube that has 1 meter on a side and make fill it with water. This is what we call 1 liter of water. That was defined around 1793 to be equal to 1 kilogram. So that's the definition of a kilogram. Sounds like a great idea. Water is the same everywhere. If you distill it and purify it, its density changes with temperature, so you have to be careful there. You have problems with wetting. So it turned out that it seemed like a good idea, but it wasn't. And so in 1799, there was a change. Here's a picture of me with an object. This object is called the kilogram of the archives. It was a platinum cylinder made to be as close as they could make it to the mass of a liter of water, because it was a lot easier to use this platinum artifact. Do you recognize the ancient practice that we had in ancient Egypt, where an artifact was made, that we had also contemporaneously in the French Revolution? We had an artifact meter stick. Now we have an artifact kilogram as well. So in 1799, the kilogram of the archives became the standard of mass for all of France. And again, in 1875, the International Treaty of the Meter decreed that there should be a new artifact kilogram called the International Prototype Kilogram. And this was made to have a mass as close as possible to the kilogram of the archives. And that, up until May 20th of 2019, was the definition of mass. The kilogram is equal to the mass of the International Prototype Kilogram. Now think about this. The 21st century, the unit of mass is an artifact, an actual piece of metal that was made in the 19th century, based on an object that was made in the 18th century. This is a scandal. For example, if you were to leave a fingerprint on the International Prototype of the Kilogram, everybody would lose weight. That is an intolerable situation. Well, nobody leaves fingerprints on the International Prototype of the Kilogram. They're very careful about the way they handle it. in spite of that care, it appears that the mass of the prototype kilogram is changing. This is a plot of the various copies of the kilogram that were made to be identical as possible to the international prototype kilogram. And you'll notice that they all seem to be getting heavier relative to the international prototype of the kilogram. Well, it doesn't take too much imagination to think that maybe the international prototype of the kilogram is the thing that's changing. Maybe they're all changing. In fact, it seems quite likely that they are all changing. But what does that even mean? By definition, the international prototype of the kilogram is a kilogram. It cannot change by law. Well, this is just an intolerable situation. We have to fix this scandalous situation that we have. And the way we want to fix it is by using the same beautiful approach that we used for the meter. So we recall that to define the meter in this beautiful way, what we did was define the speed of light. What are we going to do to define the kilogram? Well, to explain that, let's remember what is surely the most famous equation in all of history, E equals mc squared from Einstein, that the energy of an object at rest is equal to its mass times the square of the speed of light. Now let me also remind you of another famous equation, not quite as famous, and that is that the energy of a photon, a particle of light, is equal to Planck's constant times the frequency of the light. Now let's combine those two equations together, and what we find is that the mass is equal to Planck's constant times the frequency divided by the speed of light squared. What does this mean? It means that if I had some kind of a particle, say an atomic nucleus, and it emitted a photon, one particle of light, that had a frequency f that I could measure, that if I define Planck's constant, and I've already defined c, the speed of light, that will tell me how much the mass of that particle, that nucleus, changed. So this is giving you a feeling for why we can have a definition of mass by defining Planck's constant. Now, it turns out that we are not, in fact, going to weigh photons. We could, and in fact, people do weigh photons, but not well enough for our purposes. Instead, this gentleman, Brian Kibble, invented an amazing electromechanical device that we now call a Kibble balance or a Watt balance. And I'm now going to show you a movie that explains how this thing works. So, I want you to recall how we weigh things ordinarily. So ordinarily what we do is we have a balance, and that balance weighs something by, whoops, sorry, I wanted to, okay, what I wanted to do was to start this movie and then stop it, and I've done the wrong thing somehow. Okay, so it's not doing what I want. I promise you, we practiced this, and everything was working just fine. So now we're going to start this movie again. Okay. Sorry about that, folks. Okay, here we go. Now, an ordinary balance measuring an ordinary unknown mass. We have an unknown mass on this side of the balance. The way we weigh it is we keep adding known masses on the other side of the balance until the balance balances. That's the traditional way of weighing anything, and you've all done that. Now, if we continue, I want to ask you to imagine a different way of weighing that unknown mass. Instead of putting known masses on the other side of the balance, what we're going to do is put a coil of wire with some current in it and put that in the field of a magnet. And the idea is that if we know how much current is going in this coil, and if we know the strength of these magnets and exactly what their magnetic field looks like, we can calculate the force on this coil. And if we measure the acceleration of gravity, that means we know what the mass is on the other side of the balance. Now, the trouble with this idea is that it's very difficult to know exactly where the current goes in this coil because it's just hard to measure. It's inside a wire, and you can't measure inside that wire. And it's really hard to measure the magnetic field of these magnets and know in what direction the magnetic field is pointing, both its strength and its direction. And you would need to know all those things, and you can't know those things. But it turns out that there is a way around that, and here's the genius of Kibble. What Kibble said was, let's do something different. Let's take this coil of wire, and let's have leads that come from this coil and hook it up to a voltmeter. And let's move the coil. And now you see when you move the coil, it generates a voltage. This is just like a motor, okay? It generates a voltage, and you measure that voltage, and you measure the velocity of the coil when it was creating that voltage, and we call that the velocity mode. Now, the other thing you do is the same thing we were talking about before. You instead hook this coil up to a source of current, you put current in the coil, and you compare that coil to some mass that's producing a gravitational force. And we call that the weighing mode. And this is the beauty of the thing. The mass that we had from the weighing mode times the acceleration of gravity times the velocity that we had from the velocity mode has got to be equal to the current that we measure in the weighing mode times the voltage we get from the velocity mode. So each side of this equation has things we measure from the weighing mode and things we have from the velocity mode. Why are these two things the same? Because mechanical power, force times velocity, has to be equal to electrical power, current times voltage. And then we solve for mass, and we have a new way of defining mass. But remember, I promised you that this was related to Planck's constant. How does that work? Well, it works because of the quantum way of making electrical measurements. These two guys, Brian Josephson and Klaus von Klitzing, taught us that we could measure voltage in terms of E over h, the charge on the electron divided by Planck's constant, and resistance in terms of h over e squared. So when we measure the voltage in terms of 2a over h, and we measure the current in terms of resistance, h over e squared, and then the voltage again in terms of 2 over h, we find that the current is proportional to E. And when we multiply that by h over 2e, we find that the mass is proportional to h, just as I promised. And so we've made devices that do this. This device at NIST can make the kilogram, realize the kilogram, measure a kilogram to about a part in 10 to the 8th, which is better than the amount by which the kilogram changes from year to year, due to whatever it is, and we don't even know what that is. And countries all over the world are using balances like this and other methods, which I don't have time to tell you about, for measuring the kilogram in terms of the Planck's constant. And so, with all of this work all over the world, we finally redefined the kilogram on the 20th of May. But that's not the end of the story. On that same day, we changed the definition of the ampere. It used to be that the ampere was the current which, when put through two infinitely long wires, would produce a certain force per meter of those wires. Today, the ampere is defined by defining the charge on the electron. So an ampere is simply a certain number of electrons per second. Now think about what this means. It means that both the charge on the electron and Planck's constant are defined so that 2a over h, the Josephson constant, and h over e squared, the von Klitzing constant, are exact. And that means that we can do electrical measurements using these SI definitions. Now here's something that very few people know. Legally, every country has defined that the legal units of voltage are based on fixed values of 2e over h and h over e squared, and this has been true since 1990. These are not the values of h over e and h over e squared in the SI system. They are whatever people thought were the best values at the time that they made these choices in 1990. They've changed significantly since then. So what that means is that the SI electrical units and the so-called practical or legal electrical units were not the same. We were using two different sets of units, and you had to be really careful. That's not true anymore. Because of the new definition of the ampere and the new definition of the kilogram, these two ways of defining the electrical units are the same, and this solves a really important problem. Well, we're almost done. There are two more units. The mole used to be the amount of substance that corresponded to the number of entities equal to the number of carbon-12 atoms in 12 grams of carbon-12. But now it's just a number. In other words, we've defined Avogadro's number. It used to be that the Kelvin was 1 over 273.16 to the triple point of water. And now we've defined the Boltzmann constant. In other words, a very different spirit. We've defined what the energy is per Kelvin of the atomic constituents that make up whatever we're measuring the temperature of. So these are new values, new definitions of the mole and the Kelvin that really brings to a kind of completion what was started with the French Revolution. The French Revolution brought us meters and kilograms as the basis of the metric system. The International Treaty of the Meter brought us an international agreement where the entire world agrees that they will use the metric system, including, by the way, the United States, one of the original signatories of the Convention of the Meter, and the United States has been maintaining all of its measurements in metric systems ever since then. And now, on the 20th of May, 2019, the anniversary of the signing of that 1875 Treaty of the Meter, we had the biggest revolution in measurement since the French Revolution, where we are now finally free, in the spirit of liberty of the French Revolution. We are now finally free of artifact standards of measurement because we no longer have the artifact kilogram, and we're also free of a double standard of electrical measurements. The SI, the metric, and the legal amperes are finally the same. So all the base units of the International System of Units are defined by fixing values of constants of nature: the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela. Now you can keep the International System of Units in your wallet. This wallet card has all of those numbers on it. So it seems that we really have realized the dream of the French revolutionaries, that we have something that is good for all time and for all people. And in November of 2018, at a meeting of the General Conference of Weights and Measures, the international community, 60 countries now that are signers of the International Treaty of the Meter, 60 countries agreed unanimously to adopt the new definitions. And I want to show you this movie, which was shown at that meeting of the General Conference of Weights and Measures after this adoption. Now, if I can get this thing started. There we go. 60 countries in the world agreed to this, unanimously.
It took more than 140 years.
Groundbreaking science.
And the agreement from the world's scientific community. At times, it seemed
Impossible.
accurate.
Precise measurements.
Anytime.
Anywhere. Fact. We did it.
Ce l'abbiamo fatta. We have no special. Lo logramos.
Lei sia buoni.
Mr. Mama Rondo. Welcome back.
Tout le monde, j'en savais. Het is ons gelukt.
Punta salute.
Mi smo to učinili. Dokázali jsme to.
So we're now, huh?
Congratulations. Candida. Felicitaciones.
Mazal tov.
Congratulations. Sapere la Luisa. Sara. Success. Parabéns. Ongera. Omedetou. Anguida. Olexowa. Mabruk.
Kapai.
Aiko.
Felicitations. Congratulations.
Well, that event gives me hope that perhaps the countries of the world can agree on more than just the values of the fundamental constants. But we have done this. We have gotten the International System of Units wrapped up as a nice package where we're defining each of the units by the constants of nature. It seems as if perhaps we have finally achieved that revolutionary dream. But The answer is a little bit more complicated than that. We haven't quite. And it's because of time itself. Time itself is still tied to a specific atom, namely cesium, rather than a fundamental constant. It's sort of like when length was tied to krypton instead of to the speed of light. And it doesn't seem that we have a way out of that. So we are now having other atoms that are even better than cesium as timekeepers. And it appears that we will sometime have to redefine what is meant by a second. And so, for the time being, the future of time, only time will tell. Thank you very much.
Thank you, Bill, for an absolutely wonderful talk. I wish you were here in person so you could hear the applause from the campus, but I'm sure it's there virtually. So before we move on to the Q&A session, I would like to remind everybody listening on our live feed that there is a link in which you can submit your questions real time. And Bill has promised to hang around for a while until the questions run out, which could be a long time, but let's see how it goes. But I'd like to start by introducing some of our students. So first up is U.S. Navy Lieutenant Nate Redder, who studied nuclear engineering at the University of Michigan and is currently studying applied physics with a weapons concentration. He's a member of the submarine force, and he'll be returning for a department head tour following completion of his degree. So, Lieutenant, over to you.
Good afternoon, Dr. Phillips. Thank you very much for your excellent presentation. My question is concerning fundamental constants, and really seems like the primary advantage of defining all of the different units that you mentioned in terms of fundamental constants is that it's time invariant. However, how certain are we, or is there any evidence that fundamental constants remain time invariant over periods of billions of years? Thank you.
Yeah, well, that's an excellent question. And let me begin answering that question by adjusting the premise a little bit. Let's say that the speed of light changed. What would that mean? What I claim is that it's completely meaningless to say that the speed of light changed because we have defined the speed of light. It cannot change. It would be illegal for the speed of light to change since 1983. The famous Albert Michelson, a Navy guy, spent much of his life measuring the speed of light. But as of 1983, in large part because of the ability to measure the speed of light, we defined the speed of light, and from now on, you cannot measure the speed of light. If you ever had a laboratory in which your teachers claimed that you were measuring the speed of light, they were wrong if it was done since 1983, because all you were doing was calibrating your meter stick. Now, that is going to be true of any constant that has units. That if you imagine that the constants change, you could rethink what that meant by simply redefining the constants and saying that, well, I don't even know what it would mean to say that the units had changed. But fortunately, we have, in order to answer your question, we have constants that do not have units. One of the most famous is the fine structure constant. It's the constant that sets the scale for the strength of interactions of electromagnetic forces. And it's the thing that sets the scale for example, for the energy separations in atoms. But it's a dimensionless constant. In the International System of Units, its value is e squared over 4 pi epsilon naught h bar c. Okay? So it's got a lot of constants in it, but it itself is unitless. It makes perfect sense to talk about whether that constant changed. And people have been doing experiments in the laboratory. These amazing optical clocks have established that the amount by which the fine structure constant changes is less than a part in 10 to the 18 per year. Now, there have been some other experiments that have indicated that maybe the fine structure constant is changing on galactic timescales, on the scale of the age of the universe. The trouble is that those measurements involve looking into the distant past at distant galaxies that were formed shortly after the Big Bang, and looking at the spectrum of light coming from those galaxies. The trouble with that is that a lot of stuff happened on the way, and there may have been moving ionized clouds that could shift the frequencies, and so people are not in agreement. There's some indication that maybe there's some changes, but people are not in agreement. But just as one final idea, think about the fine structure concept. Let's say it's changed. Now, some people have talked about, can I then interpret the change in the fine structure constant as a change in those other constants that make it up? And my claim is it would be silly to do that for the following reason. Before the redefinition, before 2019, E and H were not defined, but C and epsilon naught were. So if you were to ascribe the change in the fundamental, in the fine structure constant to changes in the other constants, you would have to say that E or H or both changed. But after the 20th of May, 2019, E and H were defined and C was defined, so you would have to ascribe a change in the fine structure constant to epsilon naught, the permittivity of space. Well, that's just silly. Why should what date you think about this, why should that change which constant change? So that's why I say that it doesn't make sense to think about dimensionful constants changing in time. We should only think about dimensionless constants. Now, let me add a caveat to that. There are people who are smart and whom I respect, who don't agree with me. Of course, they're wrong, but I just want to, that was supposed to be a joke. I just want to put it out there that there is still room for discussion about this. I think I'm right, they think they're right, and that's one of the things that we do in science. We have the arguments, and we will probably have that argument for a few more years. Anyway, that was an excellent question.
Fabulous, and I agree. I'd like to move on to our next student. So this is U.S. Navy Lieutenant Sasha Barnett. She's a native of California, graduated in 2014 from Cal State University Maritime Academy with a BS in Mechanical Engineering, and was commissioned through the University of California, Berkeley's Naval ROTC program as a Surface Warfare Officer Engineering Duty Option, which was something I had to learn about when I joined 3 years ago. She's served aboard the USS Hopper and the USS Higgins, stationed in Pearl Harbor and San Diego. She's currently pursuing Master of Science in Combat Systems Science and Engineering. She's doing her thesis on atmospheric characterization in the land-sea interface and its impact on high-energy laser performance. Somehow she miraculously has a little bit of free time, and so she does enjoy spending her free time playing the guitar, reading, and spending time outside with her husband and her dog. Having said that, she now has a question for you, Bill.
Thank you, and thank you, Dr. Phillips, for the presentation. So speaking of scientists not being all on the same page and arguing a lot, I was curious to know, you already mentioned that the redefinition was a unanimous agreement among 60 countries, but I don't think folks really understand or can really appreciate the work that it took to get that unanimous agreement. So I was hoping you could reflect on some of the most challenging moments during that process.
Yeah, well, so you're absolutely right. There were challenges, and at various times there were people who said, "No, we're not ready. Let's slow this down." And in fact, it was slowed down. We had to have agreement between different laboratories. So before the redefinition, when those laboratories were doing those experiments that today we would call realizing the kilogram, then it was called measuring Planck's constant. So they had to all get the same value of Planck's constant within some narrow range of uncertainty on the order of parts in 10 to the 8th. And that was not easy. And then there was a competition between two completely different methods. of measuring Planck's constant. One involved the thing that I showed you, this Kibble balance. Another involved making a perfect crystal of silicon, machining it into a perfect sphere, measuring its dimensions, measuring the distance between the silicon atoms in the perfect crystal, and then measuring the mass of one single silicon atom, which is done by atom interferometry, something that's going to be applied to inertial navigation in Frank Narducci's lab, and putting all these things together to get Planck's constant, or after the redefinition, to get the mass in kilograms of that perfect silicon sphere. And people were doing that to parts in 10 to the 8. And there was a competition between which method was the one we were going to use. Well, the idea was we were going to use both, because both do the same thing. And sometimes one of them would have a better uncertainty than the other, and sometimes they would be a little bit discrepant. And so people said, no, we've got to wait until everything is right. And so finally, people agreed that it was right. Now, one of the things that made it even more difficult was that the people voting were not the scientists who were doing the experiments. The people voting were the heads of the national metrology institutes that for each of those 60 countries. Now, in general, those were scientists, but they weren't the scientists who made the measurements. And they were scientists who were operating in a highly political environment. So to imagine a case where the United States and China and Russia and England and India and Pakistan are all going to, and 60 countries are all going to agree this really represents something. So I think that it is a testament to how international the scientific enterprise is.
Gives us hope for the future as well. So speaking of international, let me introduce Lieutenant Commander of the Canadian Navy, Darrell Jervis. He is, as I said, a member of the Royal Canadian Navy. He's also in the Applied Physics Combat track. Prior to coming to NPS, he was the Combat Systems Engineer Section Head for the Submarine Force and has 15 years in the submarine service. So over to you, Darrell.
Thank you, Dr. Narducci, and thank you again, Dr. Phillips. That was a great talk. My question today, you spoke a lot about the units and defining them by constants, but one of the things that you briefly touched on but didn't really mention was the candela. How does that, what is the candela? How does that fit in with the rest of the units and the redefinitions?
Okay.
And I will, Bill, I'm sorry, I'll point that comes from one of our audience members. Darrell's question is still forthcoming.
Okay, well, first of all, I want to say, since you're from Canada, that Canada is one of our best partners and most fierce competitors in this business. Their measurements in using a Kibble balance are absolutely marvelous, and their contributions to this whole enterprise have been just great. Okay, the candela. Well, the reason I didn't mention the candela, except in passing, is that many of us are a bit embarrassed by the candela. The candela is a unit of illumination. In fact, I'm not even sure I'm even giving you the right word for it, but it has to do with how bright something looks to the human eye. So on the one hand, the candela is the most human of the units, but on the other hand, it's also the most subject to variation, since everybody is a little bit different. Now, it turns out to within the uncertainty that matters for most measurements, people don't seem to vary too much. That is, people in Europe and people in Africa and people in Asia seem to have about the same eye sensitivity curves. See, one of the problems is that the sensitivity of the eye varies with wavelength, and you're most sensitive in the green and less sensitive in the yellow, the red and in the blue and the violet. So what the candela does is it defines what illumination is in candelas. And why candelas? Because there's an historic thing. You took a wax candle and you said, this is a standard candle, okay? And then the candela is like a new candle, okay? Well, it defines the illumination produced by wavelength of light of a certain wavelength and a certain power, watts per square meter. It defines that in terms of lumens, which are basically converted from candelas by solid angle, okay? So I forget how it's even done because, you know, we don't use it much in the lab. It's the kind of thing that you need so that when you go to the store to buy a light bulb, that you know how bright that light bulb is. Even though that light bulb is, say, has a different spectral characteristic, the lumens will tell you how bright it appears. In other words, some human being sat down and said, I think that this amount of yellow light is as bright as this amount of green light. And it turns out that most humans give pretty much the same answers for those things. That's the kind of thing that goes into the definition of the candela. So you can see why I didn't really want to talk about it. So we call that conversion a constant of nature because it seems to be a constant of humans. But it's not very constant. I mean, not like other things are, not like the speed of light. But it doesn't vary enough that it matters for the lighting industry.
Okay, Daryl, your question now.
Okay, one more question then, sir. So you spoke a bit about GPS, and I just wanted to kind of, you know, talk about how stable clocks that keep second or time down to the nanosecond for long periods of time, you know, you might say, so what? But the end result of that is I have a phone that can navigate around. So given this redefinition of the kilogram and how it is reproducible, have you seen any benefits to our operational everyday lives now, or will you foresee any benefits to this in the future that, you know, something that we can see on sort of the ground level?
Okay, that's an excellent question. Before I answer it, I just wanted, I forgot to say this, and I wanted to. You are a submariner, right? And so is Nate. Am I right there? Okay, I just wanted you to know that one of my very good friends is a guy named Skip Bowman. I don't know if you know that name. Frank Bowman. He sat in Rickover's chair. And we go to the same church, and we're good friends, and I just wanted to put in that little bit of trivia. So now let's talk about how the redefinition of the kilogram has changed things, or perhaps it will change things. So the first answer is, if we did our job right, nothing changed. Because at the time the kilogram was redefined, that redefinition should have kept the mass of the international prototype of the kilogram the same. And in fact, that was what happened by definition. So on that day, the international prototype of the kilogram was 1 kilogram plus or minus 1 part in 10 to the 8th, because that was the uncertainty in Planck's constant. So it used to be, before that date, it was 1 kilogram with no uncertainty. And after that date, it was 1 kilogram with a part in 10 to the 8th uncertainty, which for essentially anybody isn't going to make any difference. Now, that's not where we are now. Now, the international prototype of the kilogram has been compared against the kilobalances. And now we have a what's called a consensus value. All the people who have kilobalances and measure their secondary standards of kilograms, which have been measured against the international prototype of the kilogram, we now have a consensus value of the international prototype of the kilogram, which is different from 1 kilogram by, I think, 2 parts per billion, okay? So less than the uncertainty before. And then its uncertainty is the original 10 parts per billion plus the uncertainty in making comparisons, which are 4 parts per billion plus 1 part per billion per year, because things drift, and until you do another comparison of all the kilograms, you don't know where they've gone. So that's where we are now. So everything is in terms of the new definition, but everybody is using the old kilograms because that's what we've got. We are now rolling out a portable, commercially operable, we hope. I mean, it's not quite commercially available yet, but it's the kind of thing that we think can be made commercially. Watt balance, kibble balance, that will be able to realize 1 gram weights at a part per million. Now you may say, well, wait a minute, you just told me you were doing kilograms to a part in 10 to the 8th. Yeah, but doing a gram to a part in 10 to the 8th can't be done. And this is because you start with a kilogram and you want to go to a gram. How do you do it? Well, I mean, it's not done exactly this way, but the general idea is that I make myself 10 100-gram weights and compare them against the kilogram, right? And then compare them all against each other. So I can find out which one of them is 100 grams or how much off it is. And then I make 10 10-gram weights. And I compare them against one of the 100-gram weights, or maybe all the 100-gram weights. And then I do the same thing until I'm down to 1 gram. That process loses you a tremendous amount of accuracy, so that people cannot generally measure 1 gram weights to a part in 10 to the 6th. That would be a microgram. And a microgram is better than you can do on a kilogram. So, but it turns out that these kibble balances, they got no problem doing that because it's all done electrically. So what it means is it's going to revolutionize the measurement of small masses. So we're not quite there yet, but this is where we're going. A real revolution in the measurement of small masses. And this is going to have an impact on people who need to measure torques, people who need to measure drugs to very high degree of accuracy when they're doing the initial trials. They apparently have to know how much they're putting into somebody. And these are in micrograms. And knowing what that is in SI units is not so easy. So these are the kinds of things that are happening today.
I find that absolutely remarkable. I had no idea. Just simply
Well,
going from the kilogram to the gram.
See, one of the things I should say is, in order to answer that question, which I'd gotten beforehand, I had to ask my colleagues at NIST who know about it.
Great. So our next student is U.S. Navy Lieutenant Karina Monroe. She is also an engineering duty officer from Las Vegas. She did her undergraduate in physics from UCLA and is currently pursuing a master's in applied physics. Her previous tour was a deputy project superintendent for the USS Mustin, chief of Naval Operations availability at Shipyard Repair Facility, Japan Regional Maintenance Center in Japan. That was quite a mouthful. So, Karina.
Good afternoon, Dr. Phillips, and thank you for your presentation. The following is a question from an audience member. They state, I understand they are considering using pulsars as a methodology of timekeeping, given that they have steady rotation rates. How would that compare to cesium atoms in terms of stability and accuracy?
Oh, wonderful. This what a great question. So the answer is, while there was a little bit of talk about using pulsars as a time standard, it turns out it's a really bad idea. Pulsars are so much more valuable as a laboratory for testing the theory of general relativity. It turns out that the pulsing rate of these pulsars, which are like binary neutron stars, okay, is not staying constant. It decreases at an easily predictable rate because this thing is radiating gravity waves. Now, you've all heard about gravity waves. It's one of the greatest things of the last few years in physics, and we're now seeing gravity waves all the time, and it's precision measurement that made that possible to make a gravity wave observatory, but that's another story. So these millisecond pulsars slow down very, very slowly. In order to see that they're slowing down, you need an atomic clock. So by comparing the pulsing of these pulsars to the very best atomic clocks, actually an ensemble of all these atomic clocks, you can see how those pulsars are slowing down, and you can test whether Einstein's theory of how much gravity wave radiation should be radiated is correct. Now, it gets even more cool than that. If you use an Earth-based system of time to look at the pulsars, you will not get a good answer. Because, again, according to Einstein, clocks keep different time depending upon the gravitational potential in which they find themselves. So a clock at sea level runs slower than a clock up on a mountain. And the best clocks in the world, which are at the National Institute of Standards and Technology in Boulder, which is about 1,500 meters above sea level, are not keeping the same time as clocks on, closer to sea level, and certainly not keeping the same time as clocks out in outer space. But that really doesn't matter. It's just a ratio thing. But here's the problem. The Earth goes around the sun. Jupiter goes around the sun. The Earth does not have a circular orbit. We change our gravitational potential relative to the sun. Now that affects both Boulder and, let's say, Paris the same way when we go around the sun. So they don't see that. But it affects us and the pulsar very differently. So they have to re-reference their earthbound time standard to the center of mass of the solar system, including all the planets. And in fact, they do a really good job of that, but it's not perfect. That is, they can see a little bit of variation, and it looks like we don't actually know the orbits of the planets quite well enough, or maybe there's planets that we don't know about yet. So there's little tiny discrepancies, but it makes for such a cool story.
Okay, Karina, would you like to ask your question?
Yes, sir. So, Dr. Phillips, my question is, when working on theory in quantum and relativity, people often set the constants h bar and or c equal to 1 in order to simplify the equations. Doing so is fine because it just puts you in a non-SI unit system. Can all of the defining constants be set equal to 1 at the same time without any contradictions?
So, I'm not sure that I even know the answer to this question, but I think that the answer is no. So let me give you an example. It's pretty common for people who are doing calculations of atomic structure in quantum electrodynamics to set h bar and c equal to 1. But they don't set E equal to 1 because in that system of units, E squared is the fine structure constant. And they can't set the fine structure constant equal to 1 because that's a dimensionless constant. It's the same in every set of units. And it's the expansion constant for series expansions in quantum electrodynamics. So how many constants you can set equal to 1 depends upon which system you want to end up in. So you can't set every constant equal to 1 because that would be over-constrained. So, for example, I'm not allowed to make E, H, C, and epsilon naught equal to 1. Or even, I can't even define them. That's not allowed. That would be an over-defined set, and I'm not allowed to do that. So I can only make E, H, and C, and that leaves epsilon naught as a constant to be determined. But before the redefinition, epsilon naught was defined, and I'm not sure if you knew that, but it was because of the fact that the old definition of the ampere effectively defined mu naught, the magnetic permeability of the vacuum. And you may have learned that mu naught was 4 pi times 10 to the minus 7 Newton per meter squared, right? Not anymore. So that wonderful, I mean, it's pretty close. I mean, it's only different by maybe a part in 10 to the 8. But that beautiful thing that you remembered from your physics class, not true anymore. And of course, because C was defined, and because C is dependent upon epsilon naught and mu naught, that meant in the old system, epsilon naught was also defined. Now, neither epsilon naught nor mu naught are defined, but they're dependent on each other. You only have to know one. You don't have to know both. So I think that the answer is that you can't set them all. Well, certainly you can't set everything equal to 1, but you have to be really careful what you set equal to 1 because you're not allowed to over-constrain the system. So in answer to this question, since I'd gotten it in advance, I wrote to one of my colleagues who does QED theory and asked him about it, but unfortunately he hasn't gotten back to me yet. And we often have discussions, he and I, this is Peter Moore that I'm talking about things like what does it mean if the fundamental constants vary? You know, if the fine structure constant vary, how is this going to change things? If the ratio of the electron to proton mass changes, how does that compare in what it would do to our understanding of the universe to the possibility that the actual laws of nature change, as opposed to the constants that we stick into them? And these are wonderful, almost philosophical questions that we keep arguing about, but we haven't come up with any good answers.
And in the process, Bill, since 3 of the students on this panel had class with me, you've now made a liar out of me because they all learned 4 pi from mu naught.
As long as you taught that before the 20th of May, 2019, you were telling the truth.
It was probably pretty close, but I think I might have erred on the side of being truthful. So, so Nate has another question to ask.
This question is from Derek Olson of the Naval Postgraduate School. Constants like the universal gas constant have been measured using acoustic techniques, for example, the resonance of a gas in a spherical cavity. Is there any work to redefine these standards, and have any been adopted by the international community?
Well, so that's a really interesting question, too. So now, it's absolutely right, and that, in fact, is still what's being done, is measuring the universal gas constant using these resonators. The universal gas constant is equal to Planck's constant, not Planck's constant, the Boltzmann constant, times Avogadro's number, right? Because the way the universal gas constant works is it PV equals nRT, right? Well, N is the amount of gas measured in moles. But if I instead said PV equals NKT, N would be the number of molecules. So the difference between these two things is just the Avogadro number, which is now defined. And Boltzmann's constant is now defined. So that means that the gas constant is now defined. So we're not measuring the gas constant anymore. What we're doing when we do that old experiment with the gas constant is essentially establishing what the temperature is. So before, what you did was you set the temperature of this of this cell to, say, the triple point of water, and then you measured all the things that you would measure and said what the gas constant was. Now it's just the other way around. You put it in contact with some thermal reservoir, you measure all the stuff, and now you know the temperature of that thermal reservoir. What I'm hoping is that in the future, what we're going to do is measure temperature by measuring the velocity of the atoms in a gas that is held at a certain temperature. We're not quite there yet, but the kinds of things that Frank and I do are just the sort of things that would be relevant to making that kind of a temperature measurement. And that's going to be so satisfying because it's really going to make temperature so atomic, which is really the spirit of the new definition.
So, Bill, I do see that time is unfortunately running short. I'm going to ask 1, possibly 2 more questions if we have time. So, one question, which I just lost. Yes, can you comment? This is from the Marine Corps Warfighting Lab. Can you comment about the fact that does the rate of vibration of certain atoms remain unchanged based on the speed that they are moving?
Now that's very good. A very good question. Again, boy, these are great questions. So this is a question that relates very much to the special theory of relativity. So what the special theory of relativity tells us is that one observer looking at a clock in a different reference frame, moving with respect to that observer at a constant velocity. So these are what we call inertial frames. Okay, so if I'm sitting in my laboratory and some atom goes past me, or some guy holding a clock goes past me at a certain velocity, I will see a change in that frequency from what it would have been if that person had been at rest, or if that atom had been at rest, for two different reasons. One is that if there is a vector component of that velocity along the axis between me and the clock, then there's what we call a first-order Doppler shift. And this happens classically. You know, if something's coming toward you, blaring a horn, you're going to hear the frequency of the horn as being higher. Okay? It's the same thing. So, and that's a huge effect. That's an effect that's on the order of a part in a million for the kind of velocities that atoms have. And we have to beat that down to a part in 10 to the 18 in the best clocks. So that means that that effect goes away by a factor of a million in the atomic clocks that we use today. And how that's done, well, it all relates to things like laser cooling and trapping. So we get rid of that. There's something left over, which is sometimes called the second-order Doppler shift, or the relativistic time dilation. Moving clocks run slow, even after you've taken out the Doppler shift. And that effect is, see, the first one goes like the ratio of the velocity to the speed of light. And for say, thermal velocities, sound velocities, that's about a part in 10^6. The other one goes like the square of that ratio. So it's more like a part in 10 to the 12. But that's still pretty big compared to a part in 10 to the 18, which is where the best optical clocks are working today. So that has to be taken into account. And laser cooling is really important for that, but it's worse than that. I mean, we have to take into account the zero-point motion, the quantum mechanical motion of a trapped thing. I mean, it's not at rest. Even when it's as at rest as the laws of physics allow, it still isn't at rest. So we have to deal with that. So yeah, it's a big deal, and it's one of the things that motivated laser cooling in the first place. The fact that these effects of velocity are huge was one of the things that motivated us to laser cool atoms. And I'll talk about that when I come in person.
And that's a great lead into my final comment. So I do want to remind everybody who's on the NPS campus to look for Bill, hopefully almost exactly a year from today. You know, COVID travel being allowing us, Bill will come and pay us a visit, and he will give us another fabulous lecture. Thank you so much again, Bill, for your time. I'd like to turn the microphone over to our president, Vice Admiral Rondeau, for final comments.
Well, thank you very much, Dr. Narducci. Bill, if you were seeing some of the comments while you were speaking, everybody's just completely wowed by this terrific presentation. And I want to compliment you for capturing, you know, it's hard to capture this kind of complexity in a way that worked across across a very diverse listening audience, and you do it brilliantly. So thank you for that. We look forward to having you back. Prior to signing off, though, sir, a few minutes and a chance to provide a few final thoughts.
Well, one of the things that I think is important to remember is how important measurement is across so many areas. We've concentrated here about how important measurement is for the military, and we haven't exhausted that at all. If you think the military isn't interested in electrical measurements, think again. This is really, really important. And so bringing the electrical measurements into this unified system and making electrical measurements absolute and straightforward is really important throughout the military. But it is equally important in the civilian sector. One of the things that I want to mention is that so much of the improvement that has happened in measurement, not just time and frequency, although time and frequency is perhaps the best example, those improvements originated with the military. the Office of Naval Research, the Naval Research Laboratory, were leaders in making these kinds of improvements, and that has improved not only the ability of the military to do its job, to know where your submarines are in the middle of the ocean when you surface and look at those GPS satellites. That's really important, but it has revolutionized civilian life as well. So here is a case where the needs of the military have profoundly affected all walks of life, and I think we need to keep that in mind. The other thing is quantum is important. Quantum is going to be the thing that drives so many new things, and we are just at the beginning of what I like to call the second quantum revolution. And this is going to dominate all kinds of technology as well as science.
Well, thank you, Bill, very much. You know, when you see the smiles on our faculty and our students, and that physics is fun, but that quantum is really our future. So I thank you again on behalf of the faculty, the staff, and the students. Thank you so much for your time today. Prior to signing out, our next virtual SGL will be in April because we have our winter quarter graduation to focus on in March. In April, our theme that month will be integrated defense, and Vice Admiral John Hill, Commander of Missile Defense Agency, will join us on April 13th. So until then, out here.
Thank you so much. It's been a pleasure.